Welcome to This Explainer. Today, we're uncovering the everyday magic happening right under your fingertips. Think about how many times you've already touched your smartphone screen today. Dozens? Hundreds? You tap to wake it up, you swipe to scroll through your messages, and you press down to type. It feels totally physical, right? Just like pressing a piano key or hitting a button on an elevator. But what if I told you that you weren't actually pressing anything at all? What if, instead, you're performing this tiny, invisible magic trick using the natural electricity stored inside your very own body? It's true. Your finger possesses a totally unique electric signature. And today, we're going to break down exactly how your devices read that signature to connect you with the digital world. Section 1. The illusion of touch. Dispelling the pressure myth. Okay, so when you interact with the physical world, getting something to happen usually requires physical force. You push a door, it opens. You press a mechanical keyboard, a spring compresses, and boom, a letter appears. So it's completely natural that when we tap our phone glass, we think our phone is feeling the physical pressure of our skin pushing down against it. But that is entirely false. Your phone does not feel pressure the way your skin does. Instead, it senses a tiny change in electricity. The glass on your phone is perfectly rigid. It doesn't flex, it doesn't bow, and there are absolutely no mechanical switches hidden underneath that your physical force is somehow activating. The entire action is actually electrical. Which brings us to a really fascinating question. If the glass isn't feeling your physical push, if there's literally no mechanical button being pressed, how exactly does the screen know your finger is hovering above or touching it? How does a perfectly flat, unyielding piece of glass know the exact millimeter where you wanted to place a comma in your text message? Well, to answer that, we have to look past the surface. Section 2. The invisible sensor grid. Looking under the glass. So if we could somehow peel back that top layer of glass on your smartphone, we wouldn't find pressure sensors. Instead, we'd find a transparent sensor grid, literally glowing with invisible electric field lines spanning across the entire screen. Imagine a microscopic, invisible net of electricity, constantly washing back and forth over your phone's display. This grid is incredibly fine and totally transparent, sitting just underneath the glass you touch. And it's constantly active. It's just humming there with a baseline level of electrical charge, waiting for something to disturb it. The absolutely crucial point here is understanding this concept called capacitance, because your screen detects capacitance rather than physical force. Capacitance is, simply put, the ability of a system to store an electrical charge. And this is the absolute core of modern touchscreen technology. That grid we just talked about, it's basically a giant capacitor. It holds a steady, known amount of electrical charge. But here is the secret. That charge changes the exact moment a slightly conductive object enters its local electric field. And guess what happens to be a fantastic, slightly conductive object, absolutely filled with water and electrolytes? You, your human body. You are a walking conductor of electricity. Section 3, your electric signature, the mechanics of a tap and swipe. Let's break this down into the steps of a single tap. Step 1, your finger touches the glass. Remember, no actual pressure is needed here, just proximity and contact. Step 2, because your finger is conductive, it actually absorbs a tiny, tiny bit of the electrical charge from that specific spot on the screen, which causes the local electric field to bend toward you. Step 3, this creates a bright point of capacitance change. The sensor grid instantly registers a drop in charge at that exact intersection of its invisible net. And finally, step 4, the system's processor measures this precise capacitance change and calculates exactly where on the grid the touch happened, instantly translating it into a software action, like, say, opening an app. All of this happens in literally milliseconds, completely invisibly. And this brilliantly illustrates that when you swipe to scroll, you aren't just rubbing your finger on glass. You're actually dragging a moving electrical disturbance across that grid. It's kind of like dragging your finger through a still pool of water and watching the ripples follow your hand. That is exactly what you're doing to the electric field on your phone. The processors in your device track that moving drop in capacitance, calculating its speed and direction in real time to fluidly scroll your social media feed or pan across a map. It's this continuous, dynamic, electrical conversation. Section 4. Testing the capacitance theory. Proving the physics. Now, the screen only responds when an object can actually change that local electric field. A bare finger works perfectly, as we now know, because you're conductive. But if you try to tap the screen with, say, a plastic pen cap, nothing happens. Plastic is an insulator. It doesn't conduct electricity, so the electric field remains completely undisturbed. The grid doesn't even know the pen cap is there. Actually, this is exactly why you struggle to text in the winter. A normal wool or leather glove usually doesn't work because it insulates your conductive finger from the screen's electric field. However, a touchscreen glove does work perfectly. Why? Because manufacturers literally weave conductive materials, stuff like copper or silver threads, right into the fingertips of those specific gloves. Those threads bridge the gap, carrying the electrical disturbance from your finger straight to the screen. So you see, it's entirely about electrical conductivity, not the physical force of the tap. Section 5. The history of touchscreens, from electromagnetism to modern displays. To really appreciate this, we have to look back, because the deep physics behind all of this goes all the way to the 19th century. Brilliant minds like Michael Faraday and James Clerk Maxwell shaped our foundational understanding of electric fields and electromagnetism. Without their theoretical work on how invisible electric and magnetic fields behave, well, none of this would even exist. Then, decades later in the 1960s, an engineer named E.A. Johnson, who was working at the Royal Radar Establishment, utilized these exact principles to describe and pioneer an early finger-driven capacitive touchscreen. He saw the potential of using human conductivity to interact with screens way back then. And today, we've taken that foundational physics, combined it with Johnson's early engineering, and miniaturized the whole shebang. This allows modern smartphones to utilize these highly complex, transparent sensor grids that detect microscopic capacitance changes instantly and flawlessly, right in the palm of your hand. As we wrap up this explainer, I really want to let this sink in. You aren't just pushing buttons. Every single tap is a fascinating, invisible exchange of energy. You are physically interacting with an invisible field of electricity every single time you send a text or double tap a photo. It's this beautiful synthesis of 19th century physics and 21st century engineering constantly at play right at your fingertips. So the next time you pick up your device, I want to leave you with this thought to ponder. If your simple everyday swipe is actually a complex manipulation of an invisible electric field, what other invisible forces in the world around you are you interacting with, entirely unaware, every single day? Keep questioning, keep learning, and thank you so much for joining me for this explainer.